So welcome back. We are discussing on the characteristics of individual DC machine. First case, we are looking at a separately excited DC machine. You know the meaning of separately excited. So this is my armature winding or stationary winding or electromagnet. I'm going to feed a separate DC supply. Similarly, I have a rotating part, which is another coil or an inductor, which is fed by another DC source. So I have two different DC sources. Then this configuration is called as separately excited machine. And I want to control the current. What I have to do practically in the lab, in the laboratory setups, you are going to see in your along with the Teresa. You will be connecting a rheostat, which is a set of resistance. You will be connecting in series between the DC source and the field winding, which is a stationary part of your machine. See, I am what the word I'm repeating: stationary part, field winding. So these are same terms. Then we are going to have another DC source, which is connected to your rotating part, which is called armature winding, again through another armature resistance. Why? We know the formula V is equal to IR, and current is given by V by R. From this relationship, what is I? I is inversely proportional to R. If R is very big, the current will come down. If R is very less, the current will go up. Why? If you go to the laboratory, your DC voltage you can't change. Impossible. It's fixed. Can you change the voltage available here? 220 volt, 50 here, fixed. I can't change that, right? This is fixed. Similarly, the DC bus bar which available in the lab is 230 volt, fixed. But I want to change the current. What I have to put a resistor in series. I adjust this resistor. If the resistance is very minimum, I give more current. If the resistor is maximum, I give less current. So this is the field magnet, electromagnet, armature winding. If I give more current, it produces more magnetic field. If I give less current, it produces less magnetic field. How I can do? By adjusting this resistor. So this test is done like this. We got a graph where first to comparison is between your flux pi and the current. So this is my current Ix. I want to control. When the current is maximum, I get maximum flux. When the current is minimum, I get a minimum flux. So in the beginning, the current is zero, the flux is zero. As the current increases, the flux also linearly increases, exponentially increases, and reaches the maximum. So what is the meaning of 1 ampere? I get 100% flux, maximum flux of the machine. But if I want to increase the flux more, yes, I can increase. I go to the point called C, where the maximum current from your field winding is 3 ampere. You get 1.25% of your maximum flux. What is the meaning? I get 100. Say 40 Weber is the 100. 40 plus 25% of your 40 Weber. For example, I'm giving this is 100% Weber. I got at 1 ampere, but I can add up 40 into 0.25 percentage. This is going to be the combination at 3 ampere. At 3 ampere. So this is for 3 ampere and this is for 1 ampere. It's clear to you? So as you increase your flux, as you increase your field excitation current, your flux also increases. Then I want to see the characteristics between output voltage. What is the output voltage I can generate? DC voltage. How much DC voltage I can generate from the output? For that, again, I go for the excitation. I keep the current minimum 0. Output voltage generated here is also 0. I keep on increasing the current to 1. I got 120 volt DC output. Still, I increase the excitation current exactly as like this 3 ampere. So 3 ampere, I got around 150 volt. So flux is also maximum. Current is also maximum at 300 ampere. This is the characteristic of your separately excited generator under no load condition. What is the meaning? No load means I will not connect anything here. This is just open circuit. It's clear to you? Under no load condition, I get these characteristics. What happened to the loaded condition, we will see later. Then self-excited generator. So self-excited, you can have a look. The same construction is the same machine. I will have two windings. I just replace now this part. I will connect here. That's it. It's clear to you. So now you can have a look. This is the field winding, North Pole and South Pole. I have the connections, and these connections are connected to my rotor. You can have a look. This is my armature. I have the two terminal. Positive is connected to the positive. Negative is connected to the negative. I got out. It's clear? Any doubt? So how the characteristics? How to do the characteristics? Again, the same principle. I'm going to connect a rheostat, and I'm going to vary the field current. How to do that? The same principle. I will change this current. What happened? If I change the current here will change. Current here will also change because look at here. This is the total current Ix. Listen here. This is the total current Ix. What is the current here? Ix. What is the current here? Let it be If. What is the current here? Let it be Ia. Okay. So Ix. What is the value? If plus Ia. It's correct. If you want to calculate what is If, it should be Ix minus Ia. If you want to calculate what is Ia, Ix minus If. It's clear to you? So here in this case, if you adjust this rheostat, the resistance, both the current will change. It's clear to you? Now I'm going to look at the characteristics. We have three different resistors. This resistors I am going to change 200 ohms, 120 ohms, and 50 ohms. If I use 50 ohms, see the characteristics of the generator. I'm going to look at the excitation current, this current, excitation current, and the output voltage. Where I take the output voltage? I take from here. This is my output voltage. Okay. I'm going to look what happened at zero excitation current. Zero excitation current, my output voltage is 0. As keep on increasing, you can have a look, linearly increases, reaches more than 160 volt at greater than 3 ampere excitation current. If the resistance is 120 ohms, you can have a look, it is shifted 0 at 0, current 0. As the current increases, steeply increases, you can have a look. It reaches the maximum value of 160 volt at less than 2 ampere, say 1.2 ampere you're reaching. For this resistor value, 50 ohms, I need 3.5 or 6 ampere. Look at for 50 ohm, 120 ohm resistors. I need only excitation current 1.5 or 3 or something. I'm right. Very less when compared to the previous. If the resistor is 200 ohms, look at here, 200 ohms, I require less than 1 ampere. If this is less than 1 ampere, I can reach more than 160 volt output here. For example, realistic case, this is the characteristic. You can have a look, more optimal characteristics. As the current increases, exponentially your output voltage also increases steadily and reaches exactly at 3 ampere. You are getting 140 volt. Still, if you want to go to 160 or above, you need to go more than 3 ampere. Maybe 6 ampere or 7 ampere only you can reach the value of 160 volt when compared to other resistors. So the resistance plays a critical role on excitation current and your output voltage. Have a look here. If you have a maximum resistance, you are shifting the current very less and you are reaching the maximum generated voltage. So the resistance having a significant effect. So if you have more resistors, you get greater voltage with minimum excitation current. This is the observation of the characteristic open circuit characteristics you observe for a self-excited generator. Any doubt? How to do that? Change this resistor. Keep this resistor 200. Test. Keep this resistor 50 ohms. Keep this resistor 120 ohms. Test the experiment. Calculate the current on output voltage. You get this score. It's clear to you? Any doubt? Any doubt about the characteristics? Can I go to the next one? Next, how to draw the equivalent circuit and loaded condition of your different generator. How to draw the equivalent circuit. So I already showed you the equivalent circuit here many times. If you give a common connection of DC power supply between the two windings, it's self-excited. If you put an additional power supply, you cut this line separately. This is the equivalent circuit. So I don't want to explain you more. So the equivalent circuit of your field winding, your DC source, your rheostat, and connected to your field winding. What is the equivalent circuit of your rotating part, which is armature? So this is the armature, and you connect to the series resistance, and this is your load resistance. So how the characteristics looks for your DC generator under loaded condition. We have seen the previous characteristic is unloaded. Now I'm going to put a resistor here. Some resistance I'm going to connect. I'm going to conduct the same test by increasing the excitation current. What happened? You can have a look at zero current. You are not having any load. What is the meaning? Open circuit. When open circuit, you get the maximum voltage, say 100 volt. Okay. Then the characteristics, you are going to increase the current near to 10 ampere. A small drop in voltage happen between 100 to 90. So this is mean you are loading. You are increasing the resistors here. You are loading the machine. When you are loading the machine, you start getting drop. The generated voltage is not 100, comes down because V is equal to IR. You get a drop. This generated voltage is, for example, 100 volt when you are not having any load. R is 0. When you keep on increasing R, what happened? The drop also increases because V is directly proportional to R. When the drop increases, you will not get 100 volt. You will get 95 volt. Under loaded condition, when you load the machine, your voltage will not be 100. It will be 5 volt drop. You get 95. So these are the characteristics. You can have a look from 100, sometimes 95, sometimes 90. So this is like for a series motor. This is for shunt motor, and this can be for an ideal compound motor. So 3 different characteristics are shown here. What is a compound motor? Look at the diagram. So you have a field winding. Look at here. You have a field winding, and the field winding has the coil. Then you have an armature winding, and these armature winding are connected additionally with a series winding. You can have a look. There is a series winding. There is a shunt winding. So a series connection, an additional shunt connection are included within the circuit is called compound motor. So compound motor, we already seen this one. I'm right. What I am going to do here, look at here. This is my DC machine. This is my field winding. This is my armature winding. Okay. I connect this through the additional winding. I create a shunt, a series. This is one type of connection. Similarly, we have another type of connections. I will show you later, but just have an idea. So this is called compound motor. Compound motor will not have only 2 windings. It will have additional winding, which is called series and shunt. They combine together and make a new model of machine for better characteristics. So this is called compound motor. Just have an idea how it looks. So we have a field winding, the field winding. Then we will have a shunt winding. Additionally, you are going to have this series winding, small winding. This is called a compound motor. If you look at the characteristic of a compound motor, you will get something like this. As it loaded, you will not get 100 volt. It comes to less than 100 volt under loaded condition. For example, if you are loading only 50%, then your voltage will be 95. If you are loading maximum to 10 ampere, it comes to 90. So a generator will not produce as like what we have seen in the previous slide. And this is the equivalent circuit, how a series and shunt looks. For example, I already showed you. So if you want a series generator, this is the series connection, and this was a shunt connection. And this is your rotating part. So this is an example how your equivalent circuit of your compound motor looks. So you have a series winding, you have a shunt winding, a combination. We will see in detail next slides, next lecture. Then finally, today's conclusion, I want to give you as an introduction. We have seen many characteristics of your motor and generators, and we have seen separately excited, self-excited, and we have understand how the constructions are done, what are the various parts. Finally, I like to conclude today. We have seen self-excited generator. This is the important for you. You don't want to read big theories. My conclusion is enough. So in case of self-excited generator, if you look at the voltage drop at no load to full load is only 15%. If you are going to use a self-excited generator, we have a series, we have a shunt, we have compound motors. All these motors which are self-excited means only one source, not two different sources. Then what is a drop? Now I'm not having any load. Okay, I get 100 volt. When it is loaded, 15% is the maximum drop. So it will come down from 100 to 15% less. So 85 volt will be the actual voltage when it is fully loaded. It's clear to you? It will not be 100. Actually, the generator will give always, for example, this voltage gives 220 or 240 volt AC fixed, I'm right. But our generator, in practical cases, it cannot generate the fixed load. Because of the load, there will be a drop and you get only 15% drop. So if you want to use in a design, I'm going to design a machine where my constraint says that, okay, a guy, you have to design a motor for an electric vehicle, car, your drop should not be more than 15%. When you start the car, you are getting full 100 volts, say. When you're driving the car, your voltage should not less than 85 volt. Then you have to prefer self-excited generator. Let you. Then one, second one is the separately excited generator. In case of separately excited generator, the same car I'm going to use at the start, I'm getting 100 volt. And the running condition, full load, full capacity, I should have only 10% drop. 10% then I can use separately excited generator. Say example, 100 volt at the start, but under running condition, I will get 90 volt. It's clear to you? So self-excited, 15% drop. Separately excited, 10% drop. So the most important is self-excited, 15%, and separately excited, 10%. What is the next conclusion? Very important conclusion. Generator manufacturers, many manufacturers are across the globe who manufacture the electrical machines, AC or DC. They will add some additional terms. As I said last slide, we have seen some series and shunt winding they will include. Then they increase the current capacity of the machine for the large applications. And these are called as compound motor. So I have only this. This is a normal motor. If I put an additional inductor here or here, clear to you? Additional one. Apart from this winding, I put a new winding here or here. Then the configuration changes. This is called compound. We will see later in detail next lecture. So what is a compound motor? Compound motor is nothing but we introduce new set of coils or windings in series or in parallel. Parallel we call it a shunt. Please note, shunt is nothing but parallel. And within the electrical machine of your shunt generator or series generator, then we call it as compound motor or over compound motor. What is the advantage? The voltage of a over compound motor is only 10% at full load. So what is the drop? Only 10%. What is the next characteristic? You will get a flat characteristics, more flat curve, not like this, much more flatter. It's like at the no load 100, but a rated condition, a 5 to 10 volt is dropping. You will get much flatter the characteristics when you are using over compound motor. That is another conclusion. Finally, I like to give you a shunt generator. In case of shunt generator, this generator, you will have 15% below in no load conditions. For example, differentially compound motor, you will have 30%. So if you are using differentially compound motor, you will have 30% drop. For example, I have 100 volt at the start with a vehicle. When I use differential compound motor, during the running condition, I will lose 30%. This is the choice. So it's an engineer. When a problem is given to you, you have the probability to choose what type of motor I want to put into the application. It's a 10% or 15% or 30%. If I'm the consumer, I say, for me, no problem. I can have 30% drop. I can use 70 volt is sufficient for my application. So 100 volt can be available no load. Full load, I can use 70 volt. No problem. Then you go for differential. But I'm very strict. I say I want 10% only drop. At the same time, I want a flat characteristics, not too steeper drops. Then I have to go for over compound motors. It's clear to you? If I say 15%, then you have to go for self-excited. It's clear to you? As a final conclusion, in detail, we will look at the next lecture because the first day, if I put everything pump on you, collapse. Before completing my conclusion, I always start without basics. I finish all the things. Now I want to know what is the principle of a generator, what is the principle of a motor. I now tell you what is the principle. What is the principle of a motor? What is the principle of a generator? I told you the same electrical machine can work as a motor, can work as a generator. I'm right. The same issue. What is the principle? What is the principle? When a current carrying conductor, listen here. When a current carrying conductor is placed in the magnetic field, I have a north pole and a south pole. When a current carrying conductor, what is the meaning of current carrying conductor? I'm going to apply. So this is my north pole. This is my south pole. This is my conductor. The conductor, I'm going to apply a voltage, plus and minus, and this is my flux. Okay. When a current carrying conductor means I'm going to apply a voltage to it. Okay. Placed in a magnetic field, it experiences a mechanical force. It start rotates. It's clear to you? It's clear to you? So this is the principle of motor. So when a current carrying conductor is placed in the magnetic field, it start rotates. It produces a mechanical force. It's clear to you? What is the principle for a generator? When a conductor, I'm not going to apply this one. I do this one. Okay, but I'm going to use another machine to rotate it. It's clear to you? Listen my words. A conductor, not a current carrying conductor, just a conductor. I'm going to rotate in a magnetic field. Like this, okay? Not like this, okay? So I can't show you. So you have to rotate the conductor in a magnetic field. What happened? There is a flux. I cut. Am I right? So when a conductor cuts the flux, the EMF will be. This is the principle of the generator. Again, I repeat you. When a conductor is rotated in the magnetic field, it cuts the flux. According to Faraday's law of electromagnetic induction, when a conductor cuts the flux, a EMF will be induced. A voltage will be available across these two terminals. I put a load, it is closed circuit, current will flow. If it is not loaded, if it is not connected with the load, only voltage will be available. So when a current carrying conductor, when a conductor is rotated in the magnetic field, a EMF will induce across the conductor. When a current carrying conductor, listen the word, when the current carrying, I apply a voltage now. I place in the magnetic field, it experiences a mechanical force. It starts process. With this, I completed today's lecture. One more problem. With that, we can wind up today's lecture in time. So the last problem, a 240 kilowatt, 500 volt, 1750 revolution per minute, separately excited DC generator as a overall efficiency is 94%. So 240 kilowatt, 500 volt, 1750 revolution per minute, separately excited DC generator as a overall efficiency of 94%. Also, the given shunt field resistance is 60 ohms. The rated current is 5 ampere. Please note this is I square power. So typing error I square R. I square R or V square by R. Three formulas for power. You know the basics, I believe. Power equal to V into I or I square R or V square by R. Then I square R loss in the armature is 0.023 per unit. Calculate rated armature current, total losses in the machine, I square R loss in the machine. So we need to calculate all these three. Answer is here readily. I given you. First one, we have to calculate what is the rated armature current. How to calculate? Solve the problem. You know the power, you know the voltage, just divide, you get the current. So what is the power? Power of the machine is 240 kilowatt. Look at the formula. P equal to V into I. Power is 240 kilowatt. Voltage is 500. You can easily calculate what is current. I'm right. Substitute the value and calculate what is the current. The current is going to be 480 ampere. Calculate. Very simple problems. Did you calculate all? You got 480 amperes. Okay. What is the second question? Total losses in the machine. Total losses in the machine. How to calculate the total loss? How to calculate the losses? Anyone? How to calculate loss? I'm right. This formula, can you agree? What is loss? What is the output you produce minus the input is the loss. I'm right. Output minus the input. So now I have to calculate what is output power, what is my input power. So output power already I know in the problem 240 kilowatt. So this is already given. If I'm correct, this is already given 240 kilowatt. I'm right. Already given in the problem. I need to calculate what is output power. How to calculate the output power? Efficiency is equal to output power by input power. You know the efficiency given in the problem, which is 94%. And you know what is your input power? 240. Multiply. You can easily calculate what is output power. First calculate output power. Output power equal to input power equal to calculate input power. Input power equal to output power is already given 240 minus divided by efficiency. Okay. Now you calculate what is input power power from here. You know the efficiency, you know the output power. Output power is 240 kilowatt. Efficiency is 94%. Calculate what is input. Output is 240 kilowatt. Efficiency is given 94%. Put it in decimal because not in percentage. You get what is your input power. Input power is 255,319 watts. Then how to calculate the loss? The loss is nothing but input power minus output power. You know what is the input power, which is 255,319 minus output power is 24,0000. You get 15,319 watts is your loss. Loss in your machine. Please calculate, utilize this time. Third step question, they're asking you what is I square R loss. This is called copper loss. Later we will discuss. But for the basic is fine. I square R loss. What is the I square loss? You already know the loss. You calculated how much is the loss you got out of your total power capacity. So you have the capacity of 240 kilowatt. 240 kilowatt. In the problem, they are asking you what is the I square or loss in the armature in per unit. They are asking in per unit for 0.023 per unit. So just multiply the per unit and find it. So multiplied by 0.023 into 240 kilowatt. The answer is going to be 5520 watts. Is okay? Any doubt? Here, typographic error, it's square, I square R. With this, I completed. Any doubts? If you have a doubt, you can approach my office or by email. Thank you all.